Welcome to the radiation revision question walkthrough. So let's make a start. Question 1. The most abundant form of radium is radium-226. Its nuclear mass is 226 and then its nucleus contains 138 neutrons. Which of the following is an isotope of radium? So an isotope has the same number of protons, a different number of neutrons. So that is a key piece of knowledge, alongside the fact that mass is neutrons plus protons. So we need to work out really how many protons each of them has. So this one here, how many protons does it have? Well, it has 226 minus 138, which is 88 protons. So which one of these has 88 protons? Well, if we do 226 minus 137, then obviously that is not going to have the same number of protons. If we do 226 minus 139, obviously it won't. If we do 227 minus 138, it won't. 227 minus 139 will also have 88 protons. So therefore, the answer is D. Question 2. All radioactive sources have a half-life. Which statement is correct? So half-life is the time it takes for half of the radioactive nuclei to decay, or something that means the same. So have a look. Let's have a look. It's half the time for the radioactive source to become safe. Well, that's a load of rubbish. It's not that. It's the time it takes for half of an atom. Well, it's not half of an atom. It's half of all of the atoms. It's half of the time. Well, it's not half of the time. It's the total time. So it must be D. It is the time it takes the activity of the source to decrease by half. So activity is the number of decays per second. So this is another way of saying the time it takes for the half of the atoms to decay. 3a. A student has made some notes on a simple model of an atom. An atom consists of a negatively charged nucleus surrounded by protons. Most of the atom is just empty space. The nucleus contains neutrons and ions. The student has 3 mistakes. What mistakes have they made? So the nucleus is not negative, it is positive, and it isn't surrounded by protons, it's surrounded by electrons. Number 2, actually that is 2, isn't it? Most of the atom is just empty space. That is correct. The nucleus contains neutrons and ions. That is incorrect. The nucleus doesn't contain ions. It contains protons and neutrons. So these are the 3 mistakes. 3b. Some nuclei are radioactive because they are unstable. The nucleus of an atom can be shown as this. Z is the atomic number. So atomic number is the number of protons. A is the mass number, which is the number of protons and neutrons added together. Equations can be used to show radioactive decay. Describe what is shown in this equation. So we've got carbon turning to nitrogen and an electron. So firstly, it's 3 marks. We need to say 3 things. So carbon turns into nitrogen. Let's have a look at the numbers. 14 goes to 14 plus 0, so the mass stays the same. What's happened to the atomic number? The atomic number increases by 1, so that's just another way of saying the number of protons increases by 1. If we've got the same mass, but a proton has appeared, what must have happened? Well, the number of neutrons in the nucleus decreases by 1. And finally, an electron is emitted. I know I've written 5 points here, but I don't think it matters. I think you should write all 5 points down to be sure of getting the marks. I would just maybe add from the nucleus, because that is important. Part C, these cotton wool buds have been treated with gamma rays. The cotton wool buds have been irradiated but not contaminated. Describe the difference between irradiated and contaminated. So irradiated, exposed to radiation, and then the radiation source is removed. The object does not become radioactive, but contamination, radiation remains on the object. Okay, so that's the key difference. All right, this comes up all the time, guaranteed easy marks. All right, for remembering this difference here. Maybe here I'll just say radioactive material. Right, but that probably doesn't matter. Question 4. Some nuclei are radioactive because they are unstable. The terms half-life and random decay are used when describing radioactivity. Explain the concept half-life. So half-life is the time it takes for half of the nuclei in a sample to decay. You could say it's the time for the activity to decrease by half. That's fine. It means the same thing. This is how I write it. Why is radioactive decay described as random? So you cannot predict when an individual radioactive atom will decay. All right, that's what it means by random. 5A, let's zoom out a little bit. Vic is investigating a radioactive liquid. He measures the count rate for a sample. Look at the graph of his results. Use the graph to calculate the half-life of the sample. So for this, I'm going to use a shape, although you should obviously write on this if it was for real. So the half-life is the time it takes for the count rate to decrease by half, the activity to decrease by half. So what is half of the count rate? Well, we start at 2000 and we go down to 1000. Can't really see that. Let's just make it a bit thicker. Okay. So it's the time it takes to decrease by half. So that's 1000. Right, I'll just put another one in. So what is the time here? Well, if we go back down to the time axis, we can see that it's about 36 hours. All right. Obviously, this line is a lot thicker than you would write on an exam in pencil, but that's how you do it. You draw the line across, down, and you read off this time here, which is 36 hours. The activity at the start of the measurement is 2000 counts per minute for this sample. How long will it take for the count rate from the sample to reach 31 counts per minute? So 2000 at the start. After one half-life, it will go to 1000. After 2, it will go to 500. After 3, 250. 125. and then it will go to 62.5, and then it will go to 31. So how many half-lives is this? So this is, we've got 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives, 6 half-lives. So this is 6 half-lives. 1 half-life is, what have we just worked out from the previous question? We worked out it was 36 hours. So how long is 6 half-lives? Well, it's 6 times 36. Oops. Which is 216 hours. Okay, now you can't look at the graph because it's obviously far too low down here, so you have to do it mathematically like this, right? But it's super easy. All right, 6A. This question is about nuclear radiation. Radioactive materials decay naturally. The half-life is a measure of how quickly the radioactive material decays. Look at the data below about the activity of 4 radioactive isotopes. And then it says, which isotope has the shortest half-life? So which is the quickest to decay by half? So it should be fairly obvious which one decays the most quickly. Well, it's obviously this line. It has a half-life of only 20 seconds, so that means the answer is A. And then explain your answer. So A decreases its count rate by half in the shortest time. And then maybe I would just quote a value from the graph, 20 seconds versus 44 for B. What I would actually probably do is draw on a line here, all right, to represent half the count rate, and then I'll say obviously A crosses this line the first and the least time. Part B, radioactive carbon-14 has a half-life of 5,730 years. Carbon-14 can be used to find out the age of some materials. Explain how. So what you need to do, you need to look at how much carbon-14 is in a material, and then you compare this amount to the amount of carbon in a living object, and then we use the maths of half-life to work out the fraction of carbon in the material, and then we can work out its age. So what do I mean by that? Well, supposing you found some a material in the ground that had as much carbon-14 as a living object did, right? Then you would know that its age is basically 0 years. Supposing you found a piece of material in the ground that had 50% of the carbon-14 that a living thing has, well, then you know that half of it has decayed, so it must be 5,730 years. Supposing you found something in the ground that had a quarter of the carbon of something in that was living, you would know that it's undergone 2 half-lives, halve it and halve it again. So it would be about 14,000 years and so on. So that's the idea behind carbon dating. All right, part 2. Wooden beams from a house are thought to be from trees cut down about 100 years ago. The radioactive dating method cannot be used to show that 100 years is the accurate value. Suggest why. So 100 years is far too short a time. Very little of the carbon will have decayed in 100 years, and then its half-life is 5,700 years. Right, so little will have changed that you just won't be able to measure it at all. All right, question 7. Let's get on one page. Greg is in hospital for some medical tests using a radioactive tracer. He tells his friends about these tests. Here are 3 things he says. Which of the statements could be correct and which must be incorrect? So, statement 1, they gave me a radioactive drink which was giving out gamma radiation. That could be true. Then a radioactive fuse detector to measure the radiation on the outside of my body. Could be true. Now that I've taken some radioactive drink, I will always be highly radioactive. Not true. So 1 and 2 are true. So gamma radiation is highly penetrating, so can easily leave the body and can be detected outside the body. 3 is not true. The radioactive material will decay inside your body, and after a while all of it will have decayed. And obviously if you're drinking some radiation, they'll pick something that has a short half-life, so it decays quite quickly. Question 9. Rosalind is studying nuclear reactions. Radioactive isotopes decay over a period of time. Look at the graph of isotope X decaying. Calculate the half-life of isotope X using this graph. So very similar to the previous question, we need to look at the percentage remaining, and when the percentage is decreased by half, then we know that is the half-life, so then we can find the time. So if we go down on the graph, obviously I'm doing a much thicker line than you would draw on in pencil, but you can see 50% results in a time of 40 years. The half-life of another radioactive isotope, neptunium, is approximately 2 times 10 to the 6 years. The sample of the isotope has a mass of 200 grams. What mass of this isotope will be left after a period of 6 million years? So 6 million years is 3 half-lives, okay? Because 6 million equals 3 times by 2 times 10 to the 6. Okay. So after 3 half-lives, what will have happened? Well, after 1 half-life, it will have gone to 100 grams. After 2 half-lives, it will have gone to 50 grams. And after 3 half-lives, it will have gone to 25 grams. So the answer is 25 grams. Question 9. Polly and Oliver were talking about the factory that is near their home. Polly said the factory produces dangerous radioactive waste. Oliver said that if waste was put into thick aluminium cans, it could be stored safely. Is Oliver correct? Sort of. But I probably wouldn't write that on my exam. All right. Aluminium or thick aluminium will block alpha and beta radiation, but not gamma. So some radiation could still escape. Some will be blocked, some will escape. In reality, they'll use very thick concrete or very thick steel or lead that will block the gamma as well. Question 10. This question is about nuclear radiations. Ben investigates the penetrating power of different radiations. Look at the diagram of results. He now puts the same absorbers in different order. Complete the diagram to show where each radiation is stopped. So let's get an arrow. So alpha is stopped by paper. If it's stopped by paper, it's definitely stopped by aluminium. Oops. Beta is stopped by aluminium, so it will still be stopped by aluminium. And finally, gamma is stopped by lead, so the only thing that will stop it is lead, like this. When nuclear radiation passes through air, it ionizes some of the gases in the air. What happens to air molecules to make them ions? So electrons are removed from the air molecules to leave them positively charged. Nuclear radiation can damage human cells. Explain how radiation can ionize DNA, which can lead to cell mutations. Or I should say, which damages DNA, which can lead to cell mutations. Question 12. Beryllium-13 is a radioactive isotope. This is the equation for the decay of beryllium-13. What is X? This question is interesting because it's trying to catch you out. So, what are the differences between the numbers? The bottom is 0 and the top is 1. So, what particle has 1, 0? Well, an alpha particle is 4, 2, so it can't be an alpha particle. A beta particle is 0, minus 1, so it can't be a beta particle. A gamma ray is 0, 0. A neutron is 0, 1, because remember the top is the mass number, protons and neutrons. The bottom is protons only, so it has to be a neutron. So it's quite a sneaky question, that, but they could ask it. 13. This question is about different types of radiation. An isotope emits one type of radiation. It could be alpha, beta, or gamma. Describe how a teacher could show the type of radiation emitted using school equipment. You may include a diagram. So if this question came up, this is the diagram that I would use. Right? And I would say, in turn, put paper, then aluminium, then lead in front of the radioactive source. So if the count rate drops after paper is put in front, then it is alpha. If the count rate drops when aluminium is put in front, then it is beta. And if the count rate drops when lead is put in front, then it is gamma. All right, but importantly, if it's beta, then nothing will happen when paper is put in front, and if it's gamma, nothing will happen when you put paper or aluminium in front. All right, pretty standard question. They love this kind of idea. So this here, very important to learn. I think that is the end of the questions.